So we're going to do a little bit more using algebra and algebra techniques for finding limits. And again, most of what we're going to do today is pretty straightforward. And then at the end are two pieces that are really important ideas that are used beyond algebra and into calculus. So I find them interesting. So if we have a polynomial, if p is a polynomial function, then the limit of that polynomial function as x approaches c is just the value you get when you plug in c for x. So because polynomial functions are defined over all real numbers, we can just plug in our value and that's our limit. With a power or a root. So if we have a limit for some function f of x, and we know what it is, it exists, it's a value. And if n is greater than or equal to 2 and is positive, so it's got to be a positive integer greater than or equal to 2. And the reason we need that, I'll explain in a minute. Then the limit as x approaches c of that function raised to the nth power is the same thing as if you took the limit first and got the value and took that value to the nth power. Same thing with roots. Okay, so a few things that are important to know. N is a positive integer. That way, if it was negative, we would get a fraction, and then we'd have to be concerned about if the denominator was 0. And then, similar to other things we've talked about, if f of x was negative, then the nth root would, and n was an even root, we just would not have, it would be the limit does not exist, and we'd be done. So still, you just have to be careful with some of these properties. All right, the fun one, the limit of a quotient. So if I'm taking the limit as x approaches c of some function f of x divided by a function g of x, I can look at the limit of the numerator, the limit as x approaches c of f of x, divided by the limit as x approaches c of g of x. So you can look at the parts as opposed to just the whole. And like I said, this limit of a quotient is one that becomes interesting, and we'll take a look at a case where it's very interesting as we look through some examples. All right, so find the limits. And we're going to do 5 of them, I think. Yep, 5 of them. Excellent. So the first one we have the limit as x approaches 2 of a polynomial, 5x to the 4th minus 6x cubed plus 3x squared plus 4x minus 2. And the property we looked at said, hey, just take this and plug 2 in for x. We still have to write the right operations down. So 2 to the fourth, 2, 4, 8, 16 times 5 is 80. 2 cubed is 8. 8 times 6 is 48. 2 squared is 4, times 3 is 12. 4 times 2 is 8. And then we have minus 2. So if we go ahead and simplify that, 80 minus 48 is 32, plus 12 is 44, plus 8 is 52, minus 2 gives us 50. The next two very similar. We're just going to take the limit as x approaches 1 in this first case. So I would use that property that says I can do the limit as x approaches 1 of 3x minus 5 and take that whole thing to the fourth power. So as x approaches 1, that would be 3 times 1 minus 5. Take that whole thing to the fourth power. 3 times 1 is 3, minus 5 is negative 2. Negative 2 to the fourth power is positive 16. Right. Again, square root of a limit of a square root is the same as the square root of the limit. So that's going to be the square root of 5 times 0 squared plus 8, which would be the square root of 8. And if we simplify that, not finding the decimal, but just writing it as a simplified root, that would be the same as 2 times the square root of 2. The reason I find quotients the most interesting is we have to be careful because we know the denominator can't be 0. So in this first case, I think we're okay. If I take the limit as x approaches 1 in the numerator, and the limit as x approaches 1 in the denominator, one cubed is 1 times 5 is 5. 5 minus 1 is 4, plus 2 is 6. And in the denominator, 3 times 1 is 3, plus 4 is 7. So if it works out to be so that the denominator is not 0, it's pretty easy. However, if you get the denominator to be 0, so if I look at this last example, limit as x approaches 3 of x squared minus x minus 6 over the limit as x approaches 3 of x squared minus 9. If I plug 3 in, that would be 3 squared minus 3 minus 6 over 3 squared minus 9. 9 minus 3 minus 6 over 9 minus 9. And we get 0 over 0. And that's not so good. Okay, bad drawing. So what we need to do is go back up to our original expression. So we're going to go up here, and instead of trying to calculate it the way it is, we're going to do some work. And the work we're going to do is going to be either factoring. If it was, if we had fractions, we'd maybe try to find a common denominator and combine some things. If it was a root, we might multiply by the conjugate. So all kinds of things that we can do. In this case, I'm going to rewrite this back as the limit as x approaches 3, and I'm going to factor. My numerator ends up as x minus 2. Nope, sorry, x plus 2 and x minus 3. And my denominator ends up as x plus 3, x minus 3. And so there's a common factor that reduces. And it's important that we reduce it out because that's where the 0 comes from. And so we have then the limit as x approaches 3 of x plus 2 over x plus 3. And I can find that limit by plugging 3 in for x. 3 plus 2 over 3 plus 3, 5 over 6. So some people, if they have the limit of a quotient, the first thing they do is factor it and cancel any common factors. It eliminates the problem of getting 0 over 0. Okay, so that you only need to do that if you get 0 over 0. If you get something else over 0, then the limit doesn't exist. If you get 0 over something, then the answer is just 0. So it actually works out pretty easy. Excuse me. And this quotient idea leads to a different or another limit, another application, the limit of an average rate of change. So this is used quite a bit. It's actually, another way to think about it is slope. So we're going to let the limit as x approaches c of f of x minus f of c divided by x minus c. And if you just look at it, pretty clear, if I plug c in for x, I'm going to get f of c minus f of c, which is 0, over c minus c, which is 0. So we do get 0 over 0, so we're going to hopefully be able to do some factoring. So if we take a look, we want to find the limit as x approaches 2 of the rate of change function, where f of x is x squared plus 3x. So x squared plus 3x. And then we need to find the value when we plug in 2. Which is 10. So that's going to be minus 10 over x minus 2. Again, first thing I would do, factor. X minus 2 is already factored, so the denominator is good to go. The numerator, two numbers that multiply to negative 10 and add to +3, +5, and -2. So again, we get a factor that cancels. And as a matter of fact, on a problem like this, because the denominator doesn't factor, you can almost guarantee that the numerator is going to have that same factor x minus 2 in it. It's a good hint. So really what we're looking at then is the limit as x approaches 2 of x plus 5, and we know we can plug 2 in for x and get 7. All right. So you're going to do just the odds 40 on page 883 for number 17 through 47. I did post a photocopy of the page for lesson 2 as well as for lesson 1 in Schoology, so they are there for you if you need it.